Assalamu alaikum everyone. This is Khalifa Alshamsi from batch 29, and in this video I'll be going over all the figures and graphs from the physiology lecture, Mechanism of Breathing Compliance. So this slide introduces the pressure volume graph, which tells us that the slope of this graph, of the change in volume over the change in pressure, is equal to compliance. This means that if the slope was high, compliance is high. So if you imagine like a line going like this, okay, this line has a high slope, so it has a high compliance. But if there was another line going like this line has a low slope or a less slope, and so it would have less compliance. The slide also says that compliance and elastic recoil are inversely related, which means that if one goes up, the other goes down. Elastic recoil, simply put, is how much an object wants to go back to its original shape after being stretched. So if you imagine, for example, a rubber band, if you stretch the rubber band, it will try to go back to its original shape, which means it has high elastic recoil and low compliance. But for example, if you take a gum, a chewing gum, if you stretch the chewing gum, it will not try to go back to its original shape, which means it has low elastic recoil and high compliance. So in this figure, we can see two things. This on the left is just describing the experiment. We put a lung in a jar and we use a pump to change the pressure, and then we just measure the amount of volume of air that's entering or exiting the lung. What's more important is this graph over here. Basically, we can see that the line for inspiration or breathing in is not the same as the line for expiration or breathing out. There is a difference between them. So the question becomes why? Why is there a difference between the line for inspiration and the line for expiration? You would imagine that when you take the breath in, you will follow this line, but when you reach up, when you're breathing out, you would follow the same line back. But for some reason, there is a difference between them. The answer to this question is because of surface tension. So, what is surface tension? Now, imagine the alveoli. We know that inside the alveoli, we have a thin layer of water. And we know that water molecules, they really like each other. They like to stick together. And so they keep pulling on each other. This pulling force is what we call surface tension. So this inward pulling force, okay, the water molecules, they're pulling inside. This inward pulling force, it makes the alveoli want to become as small as possible. So what does as small as possible mean? It means that when we breathe in and we try to expand them, they fight against us. So we need to spend more energy or more pressure to expand them. That's why you can see here that the slope is much less steep than the slope here. Because once we expand the alveoli and we defeat the surface tension, it's become easier for us to expand the alveoli more. And so you can see at the beginning, it's tough, but then it becomes easier, and then until we reach a limit, which is the maximum size of the alveoli. And then when we're breathing out, this time we're not fighting the surface tension. That's why the line for expiration is actually higher than the line for inspiration. And in fact, not only are we not fighting against the surface tension is helping us here. It's helping the natural elasticity of the lung and assuming the smallest shape possible for the alveoli. And so, as a result of all of this, we get the expiration line. It's higher than the inspiration line. And this difference between them, this is what we call hysteresis. So, this figure actually builds upon the previous figure where we can see the air inflation curve, and there's a hysteresis between the inspiration and the expiration line. But then we also have a saline inflation curve. Basically, in the saline experiment, scientists took a lung and instead of filling it with air, they filled it with saline or salt water. Why saline, you might ask? Well, because saline completely eliminates surface tension. When you have water there will be no water molecules beside air molecules. There will be no surface, so there is no surface tension. And what's the result? First, we can see that there is no hysteresis. We completely eliminated it. the inspiration line and the expiration line, they're both the same. Second, we can see that the graph, the saline curve, has a higher slope than this line, which makes sense since because you're no longer having surface tension, you're not fighting against it, which makes it easier for you to stretch the lungs. So in this figure, we can see many things going on. So let's divide it into parts to make it easier. First, you can notice on the x-axis, we have the airway pressure, okay? On the right side or the positive side, we have the collapsing force. Why collapsing force, you might ask? Because if you think about it, if we increase the pressure inside the lungs, the pressure will be higher than the pressure in the atmosphere. So air will go from high to low pressure, and so it will try to leave our lungs. So it's collapsing or deflating our lungs. But on the opposite side, in the negative side, we have the expanding force. Because if you make the pressure inside the lungs negative, more negative than outside, air will go from outside to inside our bodies. And so this will expand or inflate our lungs. We also see on the y-axis we have volume. So if you go up, you're increasing the volume, and if you go down, you're decreasing the volume. We also notice that we have the FRC over here. So the FRC, or the functional residual capacity, is how much air left in our body after normally breathing out. So if you normally and passively breathe out, you can notice that you still have some volume. We do not have zero volume. There is still some air left in our body because it's passive exhalation. We also notice there are three lines on this graph. We have a chest wall line, which is if we have only the chest wall without the lungs. We also have the lung alone. So if you take out the lung from outside the body and measure. And then we have the lung and chest wall, which is how it actually is in our body. In our body, the lung is not alone. The chest wall is not alone. They work together. So this purple line, this is what actually represents our bodies. So let's start talking about the yellow line, which is the lung. You can notice that the yellow line is actually on the collapsing force side. Why is it collapsing force? Because we know that the lung has a natural elastic recoil and it also has surface tension. So that's why the lung is on the collapsing force. We can also see that when airway pressure is zero, which is at rest, okay, the lung volume is very little. Why? Because the lung will try to collapse or try to deflate naturally. We can also see that when the volume, okay, the volume is at the FRC, we can see that the lung is trying to collapse. It's on the collapsing side. Why? Because it sees that the FRC is too much for it. So it just wants to deflate more. It wants to reduce the volume even more. Then we have the chest wall, which is at this green line over here. So we can see that the chest wall lies on the expanding force side. Why is that? Because the chest wall naturally likes to expand. It's the opposite of the lung. This is of course until a limit. You can notice that if we increase the volume more, the chest wall actually turns into the collapsing force. Yes, it's not as much as the lung, but still on the collapsing force. Why is that? Because you can imagine the chest wall, it expands, but it reaches a limit. It cannot expand more. So once you start expanding it more and more, it starts fighting you. It tells you, okay, this is enough. I don't want to expand more. And so it starts entering the collapsing force side. We can also notice that when the airway pressure is zero, which is at rest, the chest wall volume is actually higher, much higher than the lung volume. Why is that? Because as we said, the chest wall, it likes to expand, it likes to hold more volume of air, and so the resting point for it is higher than the resting point for the lung. Another thing we notice is that at the FRC, at the volume of the FRC, okay, the chest wall is trying to expand. It's on the expanding force. Why is that? Because it finds that the FRC does not have enough volume for it. It wants more. So it's trying to expand the chest wall to hold more air and to increase the volume until it reaches its resting position. Lastly, we have the lung and chest wall together, or this purple line, which is the accurate representation of our bodies. You can see that when the airway pressure is zero, the volume is actually at the FRC, which means that the FRC in our body is the resting position. What does resting position mean? It means that if you decrease the volume, okay, you're decreasing the volume, the pressure will become expanding. But if you increase the volume, okay, the pressure will become collapsing. So the FRC is the resting state of our body.
I want to add something here. There is a شد الحبل or tug of war between the chest wall and the lungs. The chest wall wants to pull to the expanding side, while the lungs want to pull to the collapsing side. At the FRC, there is a balance, an equilibrium between the two forces. No one is winning. This is why at rest, the volume of air is the FRC, not above and not below.
So this slide builds upon what we've previously took, and it shows us the changes and the compliance in terms of diseases, specifically emphysema and fibrosis. What we first notice is that in the chest wall, we only have the normal, but in the lung, we have the normal, we have emphysema, and we have fibrosis. The reason emphysema and fibrosis are not also in the chest wall is because these diseases, they affect the lung. They don't affect the chest wall. An example of a disease that would affect the chest wall would be things like obesity or scoliosis. So we can just see the normal graph or the normal line of the chest wall. But when we look at the lungs, we can see the emphysema line and the fibrosis line. First thing we notice is that in the emphysema line, the line is actually more steep. It has a higher slope, which means it has a higher compliance, which makes sense because emphysema, it destroys the elastic fibers in the lungs, which reduces elastic recoil and makes our lungs easier to stretch, more floppy. But in fibrosis, we see the opposite. We see that the line is actually less steep. It has a less slope, which means it has less compliance. The reason is because fibrosis, we have scar tissue. Scar tissue does not expand as much as normal tissue, so you will have less compliance. But what's more important in all of this is this part over here, the lung and chest wall. So, as we've taken before, in the normal line, when the body is at rest, okay, or the pressure is zero, this line over here, the volume, okay, this is the FRC, of the functional residual capacity. And we notice some changes as well under emphysema and fibrosis. So in emphysema, the first thing we notice is that at the FRC, at the level of the FRC, the pressure, okay, in emphysema is actually negative, which means that it is actually on the expanding side. Why is that, you might ask? Because as we said before, the reason the airway pressure is zero and the FRC are on the same place in the normal is because this is the balance between the expanding force of the chest wall and the collapsing force of the lungs. But in emphysema, the lungs, the collapsing force of the lungs or the elastic recoil is weak. So what ends up winning is the chest wall, not the lungs. That's why you can see at the FRC, the pressure is not zero, it's on the negative, which is the same as the chest wall over here. We can also notice that the new resting position of emphysema is at a much higher volume, which makes sense because at a higher volume, even the chest wall itself starts going to the zero and the positive pressure. And even the lungs, even though they have a weak elastic recoil, it becomes too much for them at a very high volume. So the new resting airway pressure of zero is at a higher volume in emphysema, which is also why you see they have barrel chest because their resting position, they have a higher volume of air. But now let's look at fibrosis. You can see that actually at the FRC, it's on the positive side, not the negative side. It's on the collapsing side. Why is that, you might ask? Because in fibrosis, the lung tissue is actually winning against the chest wall. It has less compliance because of scar tissue. So it ends up winning against the chest wall and bringing the pressure at the FRC to the collapsing of the positive side. And we can see that at airway pressure zero or at rest, the volume is less than normal, which is because of the strong collapsing force of the lung defeating the weaker expanding force of the chest wall. So this figure visualizes the concept of surface tension. You can see that water molecules, they're more strongly attracted to each other than to the air molecules in the center. So you can see that these water molecules, They are attracted to each other, these are attracted to each other, etc. What this causes is an inward force that tries to collapse the alveoli and try to make it as small as possible. Why, for example, inward and not outward, you might ask? Imagine these water molecules, they're like people, okay? They're together on a circle. Each person is placing his hand on the next person's shoulder. So this person, hand on the shoulder, hand on shoulder, hand on shoulder. As they're all connected, imagine them trying to pull each other on side. As they're pulling each other on side, they will try to get the smallest shape possible. So the next couple of figures show us just how much surface tension is a problem. Not only does it reduce compliance and makes it harder for us to breathe, if it's left unopposed and unchallenged, it can collapse the entire lung. So how does that work? According to the Laplace equation of the law of Laplace, pressure, or P, in the alveoli is equal to 2 times T of the surface tension over R of the radius. This means that if you increase surface tension, pressure would increase, and if you increase the radius, pressure would decrease. So let's look at this figure. Here, there is no surfactant, so there's nothing opposing the surface tension. You can see that we have two alveoli here of different size, one of them with a radius of 0.5 millimeters and the other with a radius of 0.25 millimeters. Yes, alveoli, they're very identical in size, but they're not 100% the same. There are some that are bigger than others. With that being said, let's apply the law of Laplace or Laplace equation and plug in these numbers into the equation. So let's start with the larger alveoli. You can see that P, or pressure, would equals 2 times 50 dyne. 50 dyne would be the surface tension. You can see that it's the same in the large alveoli and in the small alveoli. See 50 dyne, 50 dyne. So 2 times 50 dyne over 0.05, which is 0.5 millimeters or 0.05 centimeters, because it's dyne per centimeter. And so the answer would be P equals 2000 dyne over centimeter squared. That's the pressure. But now let's do for the smaller alveoli. So it's 2 times 50, the same surface tension. The only difference is the radius. So instead of being 0.5 millimeters, it's 0.25. So if you plug it into the equation, the answer would be 4000 pressure. Now we know that pressure, it goes from areas of high to low. So in this small alveoli, the pressure is 4000. So the air would leave from this area of high pressure and it will enter the area of lower pressure. Now imagine this with me. All these small alveoli in our body, the air is leaving them and is entering this larger alveoli. What do you think will happen? If this keeps on going like this, at the end, the lung would collapse because all of the alveoli will start emptying into one larger one. So you would imagine that the solution is to make both pressures in the large and in the small alveoli to be equal. So let's move on to the next figure. Here we introduce surfactant. What surfactant does is that it reduces the surface tension. So you can see instead of being 50 in the previous slide, okay, you can see it was 50, now it's 25. So you would imagine that, okay, we introduced surfactant, we reduced surface tension, so خلاص, we solved the problem, right? Not quite, because if you look at the equation, 2 times 25 over 0.05, this would give us 1000 pressure, which is less than the 2000 from before. But if we look at the smaller alveoli, it's the same, 25 and 25. So 2 times 25 over 0.025, this would give us 2000 pressure. Yes, it's less than before, but it's still higher than the 1000. So air would still leave the small and it will enter the big. So we're not solving the problem here. Thankfully, this is not how it actually works in our body. In our bodies, surfactant works differently in different alveoli. You can see here in the larger alveoli, let's say I have surfactant here, surfactant here, surfactant here, surfactant here. The distance between these surfactant molecules is a bit farther away. So their effect will be less because they are less concentrated. So for example, the surface tension, it was 50. and then it became 25. But in the smaller alveoli, we have surfactant here, surfactant here, surfactant here. These surfactant molecules, they are closer to each other. They are more concentrated, which means that their effect will be even larger than their effect in the larger alveoli. So from 50, instead of being 25, it ended up being 12.5. So we have a bigger decrease in surface tension. And so if you plug these numbers into the equation, you can see that 2 times 25 over 0.05, that's 1000 pressure. And 2 times 12.5 over 0.025, that's also 1000 pressure. So 1000 and 1000, the pressures are equal. Air will not leave and will not enter this. So this slide introduces the cells of the alveoli. You first have the type 1 cells. These are flat squamous cells, and they are the majority. So them being flat actually helps in gas exchange because they are very thin. The second type are the type 2 cells. These cells, larger and cuboidal, they produce surfactant. Now these cells, they are also found between two alveoli, as you can see here in the corners between two alveoli. So alveoli and alveoli. Between them you have the type 2 cell. There are two things that are unique about this type 2 cell. First, you have these microvilli over here. These increase the surface area. The second thing are these lamellar inclusion bodies, which store the surfactant. So the type 2 cells, they produce and they store the surfactant. So this slide jumps into detail onto what surfactant is and how it's made in our bodies. Surfactant isn't just one thing, it's a mixture of many different compounds. And the main ingredient in surfactant is DPPC, or dipalmitoyl phosphatidyl choline. So how is it made? First, the alveoli type 2 cells picks up the substrates of the ingredients from our blood, from the capillaries. So things like glucose, fatty acids, and choline. After picking them up, it creates DPPC, or as we said, dipalmitoyl. Dipalmitoyl because it has two palmitate, and phosphatidyl because it has a phosphate and a choline group. After creating DPPC, it stores it in the lamellar bodies for later use. Now, what's more important is the orientation of DPPC. You can see that it has two parts, a hydrophilic part and a hydrophobic part. The hydrophilic part is the glycerol and the phosphate and the choline. So you can see they are in the liquid under the water. But the palmitate of the tails, these are hydrophobic. They hate water, so they are away from the liquid and into the gas. So how does that reduce surface tension? By inserting surfactant molecules between the water molecules, you are reducing the attraction of the adjacent water molecules. It's like these two are friends, they want to hold the hands of each other, but you're blocking them by adding something in between, so you are weakening the interaction between them and you are reducing the surface tension. So this slide basically summarizes the main jobs of surfactant. The first is promoting the stability of the lung. This is what we've covered before with the law of Laplace. You can see that in the large alveoli, because they have a large radius, they have a decrease in pressure. But in a small alveoli without surfactant, because they have less radius, they will have higher pressure, which will cause it to collapse. But if we add surfactant, we are reducing the surface tension, or T, which will cause the pressure to also reduce, and so we have low pressure as a result. This would mean that we are promoting stability and we're preventing collapse. The second job is reducing inflation pressure and the work of breathing. So by reducing surface tension, we are increasing the compliance and it will be easier for us to inflate the lungs. The third job is what's interesting. It says that it keeps the lungs dry. But how? Let's imagine a blood vessel over here, okay? Without surfactant, there will be high force, high inward pulling force, which will create a somewhat of a suction effect. So you can imagine like it's not only pulling the walls of the alveoli, it will also somewhat pull the fluid from inside the blood vessel into the alveoli themselves, causing pulmonary edema. So by adding surfactant, you are reducing the pulling force and you're stopping the blood vessels of the blood from leaving the blood vessels and entering the alveoli. This will keep the lungs dry. So this figure introduces the concept of alveolar interdependence, and it tells us that the alveolar interdependence helps in alveolar stability. You have to understand that alveoli, they are not alone. They are all connected together, as you can see here. So, what will happen when an alveoli starts to collapse? Let's look at the central alveoli, okay? As it is collapsing, because it is connected to the adjacent alveoli, it's actually pulling them in. If you notice over here, they're circular, but over here they're more oval because they are actually being pulled in by the collapsing alveoli. As it is pulling them in, it's kind of stretching them, which would increase the elastic recoil, similar to how if you stretch a rubber band, it would like to go back to its original shape. As a result, after it stretches the adjacent alveoli, you can see that they bounce back. And when they bounce back, they actually re-stretch and reopen the collapsed alveoli. So this slide acts as a transition point in the presentation. Before this, we used to talk about the alveoli themselves. But from here on out, we'll start talking about the airways that connect to the alveoli. So there are two types of airflow that occur in our lungs. First is turbulent flow. It's this chaotic flow that you see here. It occurs in our large airways like the trachea and the bronchi. And the reason it's turbulent is because you're moving large amounts of air in a wide area, which causes the air to flow in a bit more of a chaotic way. The other type of flow is the laminar flow, or the smooth flow. It occurs in the small airways. The reason it's smoother is because it's in a small area and there's a little volume of air that's passing through it. There's also the transitional flow, which is not fully turbulent, not fully laminar, it's in between, and it occurs in the medium-sized bronchi. So, in this slide, we're looking at resistance against the airway generation. What I mean by airway generation is the level of the airway. So, for example, the trachea will be at generation 0, generation 1 will be like the main bronchi, and so on. And because we're looking at resistance here and not pressure, instead of using Laplace law, we'll be using Poiseuille's law, which states that resistance equals to eta, or the viscosity of the air, multiplied by the length over the radius to the fourth power. This means that the radius is actually the most important factor that determines the resistance. Because if you just double the radius, the resistance will actually decrease by 16 times. Now, you might say, and then Khalifa, just now you told me, if I decrease the radius, I will increase the resistance. But in the graph, the terminal bronchioles, which are the smallest, they have much less resistance than the main bronchi. Why is that? To answer your question, yes. If you compare only one terminal bronchiole with the one main bronchi, you're correct. The terminal bronchiole will have less radius, so it will have higher resistance. But in real life, there's not only one terminal bronchiole, there's thousands and thousands. So, yes, maybe the individual bronchiole is small, but if you add up all the terminal bronchioles together, the total cross sectional area would be very, very high. And so you have a high radius, which means you have a very low resistance. So, even though the main bronchi is larger, because you have many, many small, tiny airways here, the total is lower. But then you might ask, okay, why does the graph increase at first? Why doesn't it immediately decrease? This is because in the beginning, as you're going through the generations, you are decreasing the radius and you're increasing the resistance. And the reason it actually goes up instead of goes down is because there's not enough to overcome the change in radius. Maybe there's only like, let's say in the segmental, only around maybe 10 branches. In the lobar, we have maybe like 3. But compare this to the terminal where we have like 30,000. So yes, you're decreasing the radius and you're increasing the amount, but the total cross-sectional area is still not higher than the main bronchi. And so in the end, you have a lower radius, which means you have a higher resistance. But this is until a limit. Once you reach this point, the amount of airways that you have is just so much that it ends up decreasing the resistance overall. So this slide talks about the effect of lung volume on airway resistance. We can see that as lung volume increases, the airway resistance is actually decreasing. To understand why this happens, you must understand how the airways are. The airways in our body, they are not rigid pipes. They're flexible. They are connected to the lung parenchyma. What does that mean? Let's look at this drawing. So let's say this is the airway, and then you have an alveoli. When you take a deep breath and you're increasing the lung volume, okay, the alveoli will expand. So it will be something like this. But as the alveoli and the lung is expanding, you're also pulling up the airway. The airway is being pulled from both sides, and so you will end up with something like this. You can notice that this new airway is actually wider than the old one, and so we're increasing the radius. So looking back at Poiseuille's law, if you increase the radius, you're decreasing the resistance. So as you're increasing the lung volume and you're expanding the airway, you're increasing radius and you're decreasing the resistance. This graph also tells us why shallow breathing, where you're taking only little amount of lung volume, is worse, because you're working at an area of high resistance. But as you take more deep breaths and you have higher lung volume, you're working at an area of lower airway resistance. So this figure demonstrates what happens to our airway during forced expiration. First, you must understand what's trans airway pressure. Trans airway pressure is the difference between the airway pressure and the pleural pressure. If it was positive, the airway will be open. If it was negative, the airway will be collapsed. So you can see here 0 minus negative 5 is positive 5, and so this is positive, which means that the airway will be open. The same over here. Minus 1 minus negative 7 is positive 6. Positive means airway open. The same also applies here. But now let's look what happens at forced expiration. During forced expiration, you are compressing your chest so much in order to generate force. As a result of you compressing your chest, you're actually increasing the pleural pressure. And the increase is so high that it ends up being even higher than the airway pressure. So you can see 21 minus 30 is negative 9. Since the trans airway pressure is negative, you can see that the airway is collapsed. During normal expiration, this is not the case. Usually the pleural pressure might be around 0 and maybe little positive, but it will not be as high as this. It won't be plus 30. This only happens when you're trying to force air out. Now this is not a problem. In fact, it's the opposite. It acts somewhat as a safety mechanism in order to stop us from releasing all the air outside. So this slide introduces the concept of equal pressure point, or EPP, and describes it as the point at which the airway pressure is equal to the pleural pressure. The trans airway pressure will be 0. So if you look at the figure on the left, the EPP would be located over here, because you can see the pleural pressure is 30, the airway pressure is also 30, they're equal, so the EPP will be over here. Now, the EPP divides the airway into two parts. The part before, or the part upstream, you can see that the trans airway pressure is positive, so it will not be collapsed, it will be expanded. But the part downstream, or from the EPP to the mouth, you can notice that the airway becomes negative. 25 minus 30, so that's negative 5. Trans airway pressure is negative, which means it will be collapsed. So let's follow the journey of the airway pressure as it's traveling through the airway. First, we have the alveolar pressure, which is equal to the pleural pressure plus the elastic recoil pressure. So 30 plus 10, that's 40. As the air travels through the airway, you can see that it loses some pressure. So it was 40 and then 35. This is because of friction. So it loses as it passes through the airway. And so 40, 35, and then 30. Once it reaches 30, which is equal to the pleural pressure, this marks the equal pressure point, the EPP. But friction doesn't stop here. You can see that it also continues losing. So 30 becomes 25, which is less than 30 of the pleural pressure, which is why you can see that the airway is collapsed over here. I'd like to point out something though. Even though this airway is collapsed, it is not 100% completely collapsed. This is because you can see that the collapsing area is occurring in the main bronchi, where we have cartilage. And so the cartilage and the walls of the bronchi, they will prevent the airway from completely blocking and collapsing. So you would imagine that if the EPP occurred somewhere before for whatever reason, and the collapse happened after, where we don't have cartilage, there will be complete collapse instead of simple narrowing. The slide also mentions an important point. It says that the driving pressure for airflow is now alveolar pressure minus the pleural pressure. So what does that mean? The driving pressure, simply put, is the pressure gradient. It's what causes the air to flow in the first place. So let's say in a normal breathing out, the alveolar pressure would be around 20 maybe, and then the mouth pressure would be around 0. So that's the atmospheric pressure. So 20, that's higher than 0. Pressure goes from high to low areas, and so the driving pressure here would be 20, or the difference between these two. Now, you could say that the alveolar pressure during forced expiration, it's 40. So does that mean that the driving pressure is also 40? Because 40 and in the mouth we have 0? Not quite. This is because during forced expiration, we have a point of constriction over here. So it doesn't matter what the pressure difference from after the constriction is. So even if the pressure instead of being 0 was like -40 for whatever reason, this still will not determine the driving pressure. The driving pressure now is independent of what's happening after the constriction. The only thing that matters is the pressure gradient or the driving pressure from the alveoli to the EPP. So the alveoli pressure it's 40. At the EPP, the pressure is 30. So here the driving pressure will be only 10. It won't be 40. This figure shows you how important elastic recoil is in determining the EPP. So you can see in a healthy lung, the elastic recoil would be around 10. And the pleural pressure, let's say it's around 30 during forced expiration. 10 plus 30, this gives us an alveolar pressure of 40. And we know that as the air passes through the airway, it loses some pressure due to friction. So from 40 it becomes 35 and then it becomes 30. 30 and 30 of the pleural pressure, these are equal, which is the equal pressure point. And we know that after the equal pressure point, so this part over here, there will be negative trans-airway pressure because the 30 it will be 25, 25 minus 30 is -5. So there will be negative trans-airway pressure, which means there will be collapse. But in a healthy lung, the point of collapse occurs in the main bronchi, in the large airways. Over there, we have cartilage in the walls. So even though, yes, there will be collapse, it will only be minimal. It won't be full complete collapse because the cartilage will stop that. But now let's look at the emphysematous lung. In emphysema, we have a loss of elastic recoil. So instead of being positive 10, it's only positive 2. So if we add 2 and 30, we get only 32. So immediately after the air leaves the alveoli and enters the airway, it loses this extra 2 to the friction, and then immediately we have the EPP. We have it very early compared to the healthy lung. So the point of collapse, it does not occur in the large airway where we have cartilage. It occurs on the smaller airway where we don't have cartilage. So we get a full airway collapse. So this slide introduces the concept of the flow volume curve. And I know that at first it might seem complicated, but trust me, it's a lot easier than you think. Let's first start explaining this graph over here. We can see that on the y-axis, we have flow, which is the amount of air we're breathing per second, so liter per second. And you can see that above the line, so above 0, on the positive side, we have expiration or breathing out, and under it we have inspiration or breathing in. We can also see on the x-axis, we have the lung volume, which is the amount of air that we're breathing in or out. On the right side, we can see we have the RV or the residual volume. That's the minimum amount of air that we have in our lungs. It's over here. And on the left side, we have the TLC of the total lung capacity. That's the maximum volume of air that our lungs can hold. Now, let's start talking and following the loop. Starting from here, the residual volume. Let's say you try to take a very deep breath until you reach your maximum. You can see that at this point, your maximum, you have the PIF or your peak inspiratory flow. That's the maximum inspiratory flow you can generate. You can see that we're maintaining this maximum until we reach the TLC, which is the maximum amount of air that your lungs can hold. Now, let's go to the TLC and let's start by expirating, by releasing all of your air as hard as you possibly can. So you can see that the flow is going up until you reach a maximum, which is your peak expiratory flow. This is your maximum. You cannot have a higher force than this. But you can notice that unlike the peak inspiratory flow, you are not maintaining your PEF. You only have it for a little amount of time and then it stops dropping. So why does that happen? Unlike the PIF, where when you're taking the breath in, you're expanding the airway, in the PEF, you have the equal pressure point or the EPP, and you have a point where the airway starts collapsing. So at the point of collapse, it does not matter how hard you're trying to breathe out. The amount of air that's leaving your body does not depend on your effort. Instead, it depends on your lungs' natural elasticity and the air resistance in your airway. That's why you can see that the PEF is only for a little time and then you can see the graph going down. Unlike the PIF, where you are maintaining the inspiratory flow until you reach the TLC. Now this graph also shows us another loop. Here we're starting from the FRC, or your functional residual capacity. That's the amount of air left inside of your lungs after normally or passively exhaling. You can see that the loop over here, it's symmetrical. The inspiration and the expiration, they are the same. This is because in normal breathing, you don't have the EPP and you don't have the constriction and the collapsing of the airway. So, as a result, you have a more symmetrical loop. And of course, this is not the same as when you are trying to force air inside and outside. You can see that peak inspiration is different than the peak expiration. To better understand this concept, let's look at this other graph. This graph shows three lines. The first line is the maximum effort over here. And then you have the moderate effort or B. And then you start little or mild. And then you follow it with the maximum effort. You can notice that it does not matter your effort. At the end, the decrease in flow is all the same. This is what we call the effort independent limb. This part of the graph where you're decreasing the airflow, it's not dependent on your effort. As we said, it depends on the elastic recoil of the lungs and the air resistance. Even if you spend more energy and try your best to try to increase the flow, it won't happen. You will still have the same decrease in flow because it is independent of your effort. This is unlike the beginning. You can see that over here, this part is dependent. It depends on the effort. The more effort, you can see, the higher the peak, which is this part over here. But the second part of the graph, or this part, it's independent. It does not care about your effort. Why doesn't it care? Because there's airway compression. And so it doesn't matter if you try to force more air inside. Because there is airway compression and collapse, the flow would be the same. An example I can give you to try to imagine this better would be to imagine a balloon. Let's say you are pinching the neck of the balloon. It does not matter if you try to force air inside or use little effort or medium effort, the amount of air that's entering the balloon will be the same in all cases. The only difference is that your cheeks will start to hurt and you will use more energy. So this figure shows the changes in the flow volume loop in obstructive and restrictive diseases. So let's start by looking at the graph. The graph shows flow against the volume. Normally in a healthy adult, this is the shape of the flow loop. You can see that we have TLC or the total lung capacity, which is the maximum amount of air our lungs can hold. You can also see we have the RV or the residual volume. That's the amount of air left inside of our lungs after breathing out fully. And we can also say VC or the vital capacity, which is the difference between them both. So let's start by looking at obstructive diseases and how they change the shape and structure of this loop. Obstructive diseases are things like emphysema and asthma. There, we have a problem with letting air outside of our lungs. As a result, air becomes trapped inside of our lungs and our lungs will be hyperinflated. As a result, the loop will shift to the left because there will be more air inside of our lungs. TLC, FRC, and RV will all be increased. Another thing we notice is that there is this coving. It's like someone took a scoop out of this curve. We can also notice that the peak expiratory flow is less than before. This is because it is harder for us to release air outside. Now let's look at restrictive diseases. An example would be fibrosis, or even things like obesity and scoliosis. Here we have a problem with letting air inside of our lungs. So we can see that the loop shifts to the right because there is less air that's coming inside of our lungs. We can also see that even though there is no curving, the shape is smaller. The loop here is smaller than normal. With that being said, I hope you've benefited from this video. If there's something you don't understand or have any questions, feel free to reach out. Good luck.